Okay, so today, first, I thought I should start just kind of like maybe explain a bit the stuff of how to draw the graphs of the parabola because it is a bit easier to, like the way it said it, like it's correct, but it's kind of like I broke it into too many steps. Whereas like you can just kind of like do it after what we discussed last time, you can do it like more directly. So I kind of will tell you how to do it like more straightforward, like how I explained it last time to make it like easier. So I'll do that and then give you an example of some applications about all these parabolas and all that stuff. So just how to graph how to graph a parabola. So essentially, there are two things that you need to do. So first, just to remind you, like, the way I'm writing a parabola is an equation like y equals ax squared plus bx plus c. So that will always be the standard way to refer to a parabola. So the first thing to determine is the concavity. So there's two things that you need to determine. So the first one is called the concavity. Okay, and concavity just means to the refers to it's derived from the coefficient in front of x squared. So what you have, this is related to whether a is positive or negative. So this is related to whether to the sign of a. So there are two cases for a parabola. A could be positive or a could be negative. So if a is positive, let's go to okay. So if A is positive, you can do the face trick that I told you last time. So if A is positive, draw a happy face because like A is positive, so happy face something like this. And so that means that the parabola literally will have this shape. So this parabola is called concave up. Okay. Okay. And if A is negative, well, draw like a sad face. So sad face. I can, of course, like this is not part of the graph, like these like eyes, but it's just kind of to make it easier for you to remember, like how the face is supposed to look like. Yes.
Just want to make sure if A, the greater that A is, the sharper the.
Correct. Yeah, like the as you increase A, kind of like it starts touching more. It gets closer and closer to the y-axis. In practice, most of the time, like we'll just kind of like sketch a parabola at a time. So it's only when you're trying to compare multiple ones that kind of plays more of a role. For us, it's more like the more important thing is like whether it's up or down. Because well, I'll say why that's useful in a moment. But what I was saying here is that if A is negative, so it's kind of like a sad face. And again, like, this is not part of the graph. This is kind of just to help you draw it out. So if it's like a sad face, it looks like this. Okay, and this is called concave down parabola. The reason why the concavity is important, or whether there's A is positive or negative, is that if you just look at the graph, you know, this graph will have a like kind of like a minimum value here. There's kind of like a mean value here, whereas you know this graph will have a max value here. So if you imagine kind of like drawing like a terrain with parabolas, like this is kind of helps more like to draw mountains, right? Like this is kind of like the peak of a mountain, and this would be kind of like a valley or something that has has a mean. So the concavity is kind of like important because that's kind of what determines whether there's a max or a mean that the parabola will achieve. And you'll see kind of like, I'll do kind of an applied problem in a couple of minutes to show you how that gets used in practice, which is like a convenient thing to do. So, and if you ever have to take calculus or something like that, actually, the parabolas will play a big role in that course, and knowing this is like kind of like one of the most important things to remember from like, like algebra. Okay, so so qualitatively, like parabolas only come like in two types, either positive, like happy, sad. And then the second question is, where do you draw them on the plane? That is where you go to the vertex. So like that's the other piece of information. Okay, so all the parabolas, what I'm trying to say is that all the concave parabolas look like this. Yeah. Every concave parabola in the world will look like this. You could ask like, then the question is, where do you position it on the plane, which is what I'm about to tell you. Okay, and then all the concave down parabolas look like this. Like again, they could be kind of like very wide or like or not, but like they all like in terms of like the mood of the function, like it always if it's positive or negative. Okay, so the vertex is the second piece of data that's important because that allows you to locate where to draw the parabola. Okay, so all these points, the minima or the maxima, those are called the where that occurs is called the vertex of the parabola. Okay. So the vertex is the point where the mean or the max occurs. Point on the parabola. The mean or the max occurs. Right, so again, if you are concave up, it would be a mean. If you are concave down, it would be a max. So I gave you like last time a formula for the vertex, which I would provide, like I would give you, like, well, I'm giving it on the quiz and everything, so it's not that I'm expecting you to memorize it, but I kind of like spell it out in a more complicated way that it needs to be. What you have to remember of the vertex is just like the x coordinate value. After that, like once you know that, everything else will kind of like follow. So the important thing, like the most important thing of the vertex, so like the key fact that you need to know is that the x coordinate of the vertex is always negative b or minus b over 2a. So the x coordinate of the vertex for any parabola is always negative b over 2a. That's the crucial fact of the. So what I'm trying to say is that like these points, like for example, for this parabola, the x value of this point is negative b over 2a. For this parabola, the x value is negative b over 2a. For this parabola, the x value is negative b over 2a. It's also again negative b over 2a. Like, it doesn't matter which one I choose, it's always a negative b over 2a. Okay. What happens is like depending on the parabola, like b or a can be positive or negative, and that's why you can end up landing on different quadrants and everything. But the important thing is like the x values of all these points, like regardless of the parabola, is minus b over 2a. And once you know that, that is like these two pieces of data is enough to kind of draw any parabola in the world that you like, and that's kind of what I'm going to do right now. That makes sense. Okay, so let me do it for a couple of examples, and just to show you how this looks like. I'll do it for like both cases, but you'll see how it works. So let's say I want to sketch y. I want to sketch y equals minus x squared plus 2x plus 5. I want to sketch this parabola. Okay. So the first step that you do is identify ABC. So in this case, what is A? A is -1, B is 2, and C is 5. So A, B, C are just like the numbers, like coefficients in front of x squared, x, and like the constant term respectively. So that's always how you're supposed to read that. Okay. Yeah. Okay. And then the next step is that we see that this is a negative value, right? That concavity, right, like is determined by this number. So this is negative. So whatever this parabola is, it will look like concave down. Concave down again is sad, so it will look like this. So this is how it looks like. It's just like where do we position this on the plane? That's the entire question, right? Like where do you place this on the xy plane? So this is how this is going to be the shape of this parabola. So this is like the basic shape. So it's kind of like you have like this space and you're just going to try to move it like somewhere in here, okay? And so where do you place it? Like that's where the vertex comes in. So what is a vertex for? So what is the vertex for this parabola? And what I was saying is that you only actually need to remember like the formula for the x value. So what is the x value of the vertex in this case? Well, it is always negative b over 2a. What is in this case this number? So this minus sign is always like from the formula. So b happens to be 2 here. There's this like this 2 also is from the formula, and then a happens to be -1 here. Okay, so you get well, the numerator becomes -2, and the denominator also becomes -2. So -2 divided by -2 is just 1. Okay. So what that means, like what I'm trying to say is that this is the x value. So where is x equals 1? X equals like this is 0, 1, 2, 3, 4. X equals 1 is here. So our parabola, the one that I'm trying to draw, the parabola that I'm trying to draw has like the vertex aligned somewhere on this line. So I'm going to erase this in a second, but like what that means is that the parabola could look like this, or could look like this, could look like this, could also look like this, or like this. Like we're kind of trying to decide which of all of these parabolas it is. But at least now I know that for sure it is aligned with this x value because it is supposed to have x value equal to 1. Is that making sense? So now how do you determine where to place it along this line? That is where you have to go back to the formula because the y, you have to find the y corresponding to this x value. So what is the corresponding y value? What is the y value? So remember that y is -x squared plus 2x plus 5. but we're saying that x, it happens to be one, so y is. Let's put x equals one here. Okay. So. The one squared equals one, so it's -1. 2 times one is 2, and then 5, you get that. So that gives you, okay, so this is 7, and subtract 1, you get 6. So you get y equals 6. So what I'm saying is that you have x equals 1, let's call this x. So x had to be 1 and y had to be 6. So here's 1, here is 6. So this is the vertex. And then you draw like a sad face, where the max of the face is here. So you draw. And that is how the parabola looks like. Yeah.
So the other coordinates wouldn't matter as long as you draw the side face, right?
Correct.
All of these.
Exactly, yeah, basically. Yes. Makes sense. So it's kind of like, first, like again, like this tells you, are you happy, sad? So that's the first thing to look at. And then you just like, it's kind of like, yeah, it's just like, where do you just move around the face on the plane? And then you just have to move it so that the max or the mean have coincides with the vertex, okay? So this is how this one. Does that make sense? Let me do it for like the other case where it's like the sad face, but you'll see it's like, sorry, the happy face, like the concave one, but you'll see it's kind of essentially the same idea. In fact, I'll do one that a bit easier, but it's kind of useful. Let's do sketch. That's another one that you could have. So, again, A, B, C are the coefficients in front of x squared, x, and the constant term. So the coefficient in front of x squared is 2. What is a coefficient in front of x? That can be a little bit confusing because there's no x in the formula. So that just means that x is being multiplied by 0. So the coefficient in front of x is secretly 0 because, you know, you can always, 0 times x is always 0. So like you kind of like don't write it out when something is being multiplied by 0. So if there's no x present, that's why I wanted to do this example. If there's no x in the formula, that just means that the coefficient in front of it is 0. But it's kind of always there. It's like just like being multiplied by 0, like it kind of disappears. And then C, like, oh, let's actually put like a negative value. Doesn't matter. Like that doesn't make much of a difference. Or -3. And then just to make sure, like make it clear that it could be positive, negative, it can be any number. And then C is like -3. That's the constant there. Okay. Does that make sense? So again, like if there's no x, it's just like b equals 0. Being no this number positive, right? So this is positive. Again, like you have the positive thing. So this is going to be concave up, and now it has a mean. Okay, so this is. So it is the same problem as the one we just did. Basically, it boils down to where do you draw this happy face on the xy plane, and that's what the vertex tells you. Okay. So what is the x value of the vertex in this case? Well, the x value for the vertex is always negative b over two a. That regardless of the parabola that you have, that's always the case. So b happens to be 0 in this case, which is makes our life way easier, as you'll see. But let me just write everything down. So you get 2 times a, and a is 2 in this case. So it would have been like this. So it's like negative 0 over 4. I mean, just the fact that the numerator is 0 makes everything 0. So the x value for the vertex is just 0 in this case. Is that okay, everyone? And so again, it's kind of like, okay, so x value 0 is here, so you just have to draw a happy face, right? And so it all boils down to, there are a bunch of options for what a happy face will look like. So it's just like, which of these ones do you choose? And for that, you need the y value, right? So you ask exactly the same question as before. You ask, what is the y value? How do you determine the y value? You go to the formula for the parabola. In this case, x happens to be 0, so you get 2 times 0 squared minus 3. Okay, so like 2 times 0 is 0, but like you get 0 minus 3, so you just get negative 3. So what that means is that the vertex is 0 comma negative 3. So let's put this somewhere in here. This is 0 comma negative 3. Perfect. And so then you draw like a happy face whose minima, the bottom of the face is coincides with this vertex. Okay. Again, like whether you kind of like do it like very wide face or like kind of closer to the y-axis, that's less important. The qualitative feature is what you really want to know about this is like, is it up or down, and where is the bottom or the max? That's all that you care about. If you had drawn this, like I'm about to erase it, but if you had wanted to draw this like this, like kind of closer to the y-axis, that's fine. That's up to you. Like that's not as important as just like for that, you would need to actually draw more points, like but that is not like the crucial piece of information about the parabola. The parabola, what you really want to know about a parabola is like concave up or down, and where does the max mean occurs. Okay, that's like the only two things that like you really care about. Everything else is kind of like I mean, sometimes it's also useful to know where it crosses the x-axis, and for that, you cross the x-axis when y equals 0, so you would like set the equation equal to 0. That's maybe another important thing, but at least in terms of the actual sketch, like this is more than enough for our purpose. So I think like that is kind of like maybe hopefully like an easier way to think about how to do the sketch. You identify concave up or down, and then you just find the x value for the vertex. And once you have the x value for the vertex, you find the y value, and that like more or less determines everything that you need to know. Now, like what I do want to do is kind of like at least show you how these parabolas can be useful in practice. So like I'll do like an applied problem involving a parabola, so that you get like the feeling for how this works out. Again, like that is kind of like a preview if you ever take calculus of the sort of questions that you do in calculus. That's kind of like the example I'll do right now is kind of like the bread and butter of calculus. Like a lot of problems are just exactly like of this sort. But the one that we'll do is kind of with parabolas, which is like the reason why we can solve it. So here's an applied problem. So like just to make the numbers kind of like easy to work with, let's say you have a wire which is 40 feet long. So you have a wire. wire. Oops. Forty feet long. Okay. And with that wire, think about it as a cable or a piece of string. With that, you want to make you want to build a rectangle. So you want to make using all of the wire, you want to build a rectangle. All of the wire. Okay, so just to kind of make it more concrete, to make it more clear what I'm trying to do. So here's one rectangle you could build. So for example, like you could make a rectangle, two sides equal to 5 feet, and the other two sides equal to 15 feet, because 5 plus 15, that's 20, then you get 25, and then you get 25 plus 15, which is 40, right? So all the sides add up to 40, which is like the condition. So like just imagine that you took the wire and you kind of like play with it until it makes it rectangle. So that is a possible wire, possible rectangle you could do. Here's another one you could make. You could make, like, you could make like a square is kind of like a special case of a rectangle. So you could make a square, which is what, 10, 10, 10, 10, right? That's another rectangle. Like if you add up all the sides, you get 10 plus 10 plus 10 plus 10, which adds up to 40. So like it kind of satisfies the condition. Like just to kind of like do another one, a different one, like you could do, what, let's do something like this. You could do 218, 218, right? So like that's still 2 plus 18, that's 20, then 22, and then with other 18 that adds up to 40. So all that I'm saying is that, with the same piece of wire, you can build different rectangles, right? Like all having the same like perimeter, which is how you refer to those. So now what's like kind of interesting about this problem? What's interesting is like each of these rectangles actually has a different area. So for example, like the area of a rectangle is base times height. So 15 times 5, that is 75. So the area here is 75 square feet, for example. This one, 10 times 10 is 100, right? So like the area for this one would be 100. 2 times 18 is 36, right? So the area would be 36 square feet, right? So what's kind of like interesting about the problem is like the perimeter, right, is the same, or like the length of the size is the same in all those three rectangles, but the area is actually pretty different, right, in all of them. And that is like actually like a concrete problem, right? Because if you think of the wire, you just imagine making the numbers larger. Like if you thought about the wire as kind of like fencing material, so you have like a big terrain, you want to like kind of fence part of it, like make in the shape of a rectangle. And you may want, if you want to plant something like grow tomatoes or whatever, like you may want to have as much as square footage as possible, right? For the same amount of material used in constructing the fence, right? Like, and so it would make sense to try to choose like the dimensions that give you the maximum area, right? So the question would be, one, what size of the rectangle will give you the best, like the largest area possible, right? What size should you choose for the rectangle? Should you choose? To give the largest area possible. Um, is the question making sense? What we're after. So you're trying to find the dimensions that will make these numbers like the rectangle, like the area, the largest possible. If you have seen this before, like actually the answer has to be the square. So the square is like the best solution, but we have to kind of like see why it is the square, and it will be because of a parabola. So it's kind of like that's where like the parabola kind of secretly comes in, which is kind of nice. In fact, like just like for someone if it's interested, if I have said, well, it doesn't need to be necessarily a rectangle. You could if you can say like it can be whatever shape in the world you want. It could be like this weird thing, or it could be a triangle, or it could be like a pentagon, as long as like the sides add up to 40 feet, actually the solution is a circle. So if you want to maximize the largest area and you have no restrictions on what the shape is for the fencing, like the perimeter, like you have to choose a circle. And that actually requires like very powerful calculus thing. To kind of like show that it's a circle, like why it has to be a circle, it's not like an easy thing, like you need like a lot of tools. But like that kind of explains probably a little bit if you look at the Middle Ages, like like these castles or like the middle, like how they built it, like it always was some sort of like town which was circular, right? Like someone is watching Game of Thrones or House of Dragons, like it's kind of like like most of like the Middle age constructions, like for like fortresses, are kind of like in a disk, and that makes sense if from this perspective, because that would be the region that would equal the most area for like the same amount of order material. And this was known by like the Greeks, and like they kind of knew this like result. It's just that they couldn't prove it because they didn't have calculus, but they kind of intuitively knew that it had to be like this, or like a circle. But like at least the rectangle case, it can be done with like parabola, so like that's why I wanted to bring it up. But let's kind of show you, let's see why this works. So why is this, how to find this? Find this. Okay, so I have a rectangle. I don't know what the sides are. I'll just call them X and Y. So let me call this X, Y, and Y. Okay, so X and Y are the sides of the rectangle. Like the only thing I know about X and Y, well, first, maybe I should say this. What is the area of this rectangle? The area is base times height, right? So like the area is X times Y. Okay. So I'll call A for area. So this is going to be the area. X times Y. Okay. What is the only thing I know about X and Y? It's essentially what I have been drawing here, like that when you add up all the sides of the rectangle, you get 40 feet because we're trying to build a rectangle 40 feet long, right? So the only thing I know is that the sides add to 40 feet long, right? Add to 40 feet. So what does that mean? Like what are the sides there? Like y plus x plus y plus x, right? So y plus x plus y plus x has to be 40 feet. So that, which you can kind of write a little bit nicer, like as 2y plus 2x equals 40, right? And well, you can multiply if you want by 1/2 on both sides of the equation, because like, there's a 2 in front of everything on the left side. So you get y plus x equals 20. Okay. And which is kind of how I was choosing the size for these rectangles. I was just checking that like the two sides like would add to 20 feet, like one like the base and the height. And so that allows you, it actually allows you to solve for y. So you can like out with this like in color. This is 20 minus x. So this gives you like a formula for y in terms of x. Okay. Okay, that's 12%. Okay. Well, it's kind of so. Why is that useful? Okay, why is that useful? Because of originally the area it was given in terms of x and y, but you have y in terms of x. So now you can think of the area just exclusively in terms of x. So what is the area of the rectangle? What is the area formula? The area formula was area equals x times y, but I just found that y is 20 minus x. Right? So what is this? This is 20x minus x squared, right? 20x minus x squared. And so what does that mean? That means that the area, like, sorry, forgot the x here. Like if you multiply, you get 20x minus x squared, right? So that means that the area formula is, let me write it in this way, starting with the x squared term. So it's negative x squared plus 20x. Okay. Now, does anyone recognize this thing? That's how the parabola starts, right? It's like something times x squared plus something times x. But here, a is -1, b is 20, and c equals 0, right? The only difference with the previous problems that I was doing, and that is kind of one of the things about calculus that if you ever take it, you will get used to it, is that instead of calling like y this axis, you would call it a for area. But it's kind of like, it's essentially the same as, as what we had before. So it's just that, like, I have been calling this variable y, but it's essentially the same idea. It's just like, instead of referring to it as y, I'm calling it a. So if you think about that, what does that tell you? It tells you that this is a concave down parabola, right? So this parabola is concave down because of the minus sign. And what is the vertex? The vertex, if you remember the x value, is negative b over 2a. So you get negative b is 20 over 2 times a is -1. So you get negative 20 over -2, and so you get 10. So x equals 10. Okay. And for this value, what is the area? The area for this value of x. What is the area? The area would be negative x squared plus 20x, but that becomes negative 10 squared plus 20 times 10. So it's negative 100 plus 200. So this is 100. So that means that a parabola in this case looks like this. So like what's kind of like you need to get used to it in this case is that here that's telling you that for this value for x, for this choice of x, what's the corresponding value for the area? which is what's being measured now by the vertical axis. So what this is saying is that the area reaches its maximum value if you choose a side, one of the sides of the rectangle to be 10. But if you choose one of the sides to be 10, what is the corresponding value for y? Y is 20 minus x, right? So, one of the sides of the rectangle has to be 10. One of the sides is 10. And y is 20 minus x. So that's 20 minus 10, which is 10. So that tells you precisely what I mentioned before, which is you have to use a square. Okay. So maybe it wasn't super obvious, like when I set up the problem at the beginning, like, where the parabola would come in, but what ends up happening in this case is that when you write the formula for the area in terms of one of the variables, you get a parabola, and that is what locates for you the maximum area possible. Okay, so that is actually in practice like how you would think about parabolas. And there are other problems that kind of fit exactly the same format. So like again, if you throw like a chalk in the air, that the position as a function of time is described by a parabola. And that's kind of what Galileo found. And then like, because it's a parabola, you can find the max or the mean like using this formula for the vertex. And so there are like actually surprisingly many problems that can be kind of like massage into a parabola problem. And it's kind of like cool to see it in practice how it plays out. So I thought like at least, to give you like, this is not like the focus of the course, but it's a good like a reason why like we kind of spend so much time talking about parabolas, because they do pop out in many different places. Where you may not have expected it, like, because maybe when you look at this problem, you don't think where is like the parabola here. So you do, sometimes it's not in plain sight, but you can kind of get to like an interesting formula that ends up being hard. And then questions about this. Oh, so that's what I have to tell you for today.